neural networks are pretty much everywhere, powering everything from our photo apps to these massive language models. But they've got this one massive problem. They're basically a black box. We know they work, but a lot of the time we have no clue how. So what if we could change that? Well, a really fascinating new paper proposes a radically different way to build AI, Kolmogorov-Arnold Networks, or CANs. Just imagine that for a second. I mean, instead of this tangled, confusing mess of millions of numbers, what if we could actually peek inside a trained network and understand the logic it learned? This is the huge problem CANs were designed to solve. Okay, so today's standard networks, you've probably heard of them, multi-layer perceptrons or MLPs. They're built on something called the universal approximation theorem. And that's a fancy way of saying they're guaranteed to be powerful enough to learn basically any function you throw at them. But, and this is a big but, that power comes at a cost. They can be really inefficient, needing just enormous numbers of parameters, and trying to figure out their internal logic is next to impossible. So how do CANs get around this? Well, their inspiration is really cool. It doesn't come from biology, like you might think, but from this beautiful piece of mathematics. It's a totally different foundation than what MLPs are built on. All right, it's called the Kolmogorov-Arnold representation theorem. Yeah, I know, it's a mouthful, but the core idea is actually stunningly simple. It says that any super complex function with lots of variables can be broken down into just two simple things, a bunch of simple functions that only have one variable, and just adding them together. That's it. It suggests all that complexity can be built from really simple pieces. So how does that theorem actually change the network's design? Think about it. In a standard MLP, you have simple numbers, the weights, on the connections, right? And all the heavy lifting, the complex stuff, happens at the nodes with those activation functions. KANs totally flip that script. The nodes in the KN, they just add stuff up. The real magic, the learnable, adaptable functions, they live directly on the connections themselves. And look, this isn't just some tiny tweak. It's a complete, fundamental rethinking of how a network even computes. It really boils down to what's happening on the wires that connect the network's neurons. Okay, so here's the best way to think about it. MLPs, the ones we know and love, they have numbers on the wires. Each connection is just a single number, a weight. But CANs have entire learnable functions on those wires. The network isn't just learning, say, multiply by 0.7. It's learning a whole relationship, an entire curve for each and every connection. So you're probably asking, okay, how does a network learn a function? What does that even mean? Well, it uses this really neat mathematical tool called a B-spline. And the easiest way to picture a spline is to think of it like a flexible piece of wire. You can bend and shape that wire by just moving a few key control points. So by adjusting those points, the network can shape that wire to match pretty much any curve it needs. It gives each connection this incredible flexibility and precision. Okay, so we've got these learnable functions on the edges. Kind of cool, but so what? What's the big payoff? Well, the first big wow moment is just how incredibly interpretable they are. Let's walk through an example. You've got to see this in action. So let's put this idea to the test with something called symbolic regression. We're going to generate a bunch of data using a hidden formula. In this case, it's f of x, y equals exp sine of pi x plus y squared. Now, the challenge for the CAN is not just to predict the right answers, but to actually look at the data and rediscover the original formula we used to create it. So we kick things off with a KNN that's intentionally a bit oversized, a bit more complex than it needs to be. And at first, yeah, it's just a complex mess. It looks just like a standard black box MLP. You really can't tell what's going on inside it all. But here's where the magic happens. As it trains, a process called sparsification basically encourages the network to figure out which connections are actually important and which ones are just noise. The useless connections just fade away. The network literally prunes itself, simplifying its own structure down to only what's absolutely essential. And what you're left with is this. The final prune CAN is incredibly clean. I mean, you can literally read the formula right off the network's connections. This edge learned a sine function, this one learned how to square a number, and this final one learned an exponential. The network didn't just fit the data, it figured out the exact symbolic structure we hid in there. It's totally transparent. Okay, so that interpretability is mind-blowing, but that's not the only trick CANs have up their sleeve. It turns out they can also be way more efficient. They're not just about being transparent, they're about being smarter, not just bigger. Take a look at this. On tasks where they have to fit a function,
KANs consistently get better accuracy than MLPs, but, and this is the kicker, with far fewer parameters. They're actually learning the underlying structure of the problem, not just brute forcing it with millions and millions of weights.
And this efficiency, it points to something even deeper, something called neural scaling laws, which is basically the science of how much smarter a model gets as you make it bigger. And the theory suggests CANs scale way, way better than MLPs. Their scaling exponent is 4, and all you need to know is that a higher number is better. This means that as you make a CAN bigger, it's predicted to get smarter much, much faster. Okay, this all sounds pretty incredible, right? Like a silver bullet. But it's really important to be realistic here. This is a very new idea, and CANs have some pretty significant hurdles to clear before they're ready for prime time.
Probably the biggest hurdle right now is just pure speed. Training a CAN can be up to 10 times slower than a similar MLP, and that's a major bottleneck for anyone doing research or development. Plus, it's still a huge open question whether they can scale up effectively to the massive, massive size of today's big AI models. But you know what? Maybe replacing MLPs isn't even the most exciting part of this story. The authors themselves propose a different vision. What if CANs could be a collaborative partner for scientists? They put it perfectly, saying, when a human user stares at a CAN, it is like communicating with it using the language of functions. That's a powerful idea.
And hey, this isn't just some abstract idea. They've already put it to the test. Early experiments have shown CANs acting like a real scientific partner, helping to rediscover these complex relationships in knot theory and precisely identifying phase transitions in physics. They're already proving they can be a powerful new tool for discovery. So this all leaves us with a really fascinating question, doesn't it? Are CANs the next evolution of AI, destined to replace today's black boxes? Or is their true power as a new kind of microscope, an interpretable tool to help accelerate human scientific discovery? Maybe the answer is both. I'm really curious what you think. Is this the future of deep learning or just a beautiful mathematical idea that's still searching for its killer app? Let me know your thoughts below. Thanks for watching.